Okay, so I will be talking to you about key quality parameters in hyperspectral remote sensing. I've been having talks about key quality parameters in hyperspectral systems for 15 years now. So if you have seen others, there might be some reuse of slides, just so you know, but here I also cover more of the operational side as well. I will go first through everything that has to do with the camera itself, which is a lot of information. Then we can maybe stop after the camera part and some questions, and then take the operational consideration afterwards. What is hyperspectral imaging? That was mentioned in the last presentation, right? And as I also mentioned, there are many types of optical architectures. But the goal is the same, to make pixels where you have several, for hyperspectral, hundreds of colors or bands. So if your main focus is quality, your highest priority should always be spectral fidelity in each pixel. We are using push-broom architecture. We believe this is the optimal architecture for remote sensing from aircrafts, because you have the movement of the aircraft and you're gathering all the spectral information at the same time. So you don't need to do any reconstruction to actually generate a spectra, but you have to reconstruct to generate a spatial domain, which we are going to show for georeferencing and auto-rectification tomorrow. Yeah, so basically you are capturing a very narrow slit or line on ground, spatial line, and you're capturing all the spectral information at the same time. So to build up a 2D spatial image, you have to either scan the camera or scan the scene. So in airborne, of course, we are scanning the camera. And to reconstruct that data, then you need to know the exact position of every line that you're scanning. So you need to know X, Y, Z, roll, pitch, and heading for each frame. And that's that we are going into that in the operational part afterwards. Here's just a very rough schematic of the classical systems, where you have an entrance aperture, focusing mirror, you have a slit that is basically capturing out the very narrow scene on ground. You have a mirror collimating the light onto a dispersive element, and you have some relay optics, which is focusing the nozzle onto an FPA. Yeah. This is a typical data sheet of a hyperspectral system. This is for our Mjolnir systems, I see, our drone systems. So this is what you can see in a data sheet when you want to buy a system, or when you want to look at what kind of quality your system or what kind of specs your camera has. This tells you about the spectral range of your system here. Visible range, shortwave infrared range, tells you how many spatial pixels you have. Yeah, you can combine it here as well. How many bands you have with different samplings, 5.1 nanometers for the shortwave here, 3 nanometers for the visible one. The F number, I will also come back to that for a hyperspectral system, what the F number means. The field of view, instantaneous field of view, and bit resolution, noise floor, dynamic range, peak SNR, and max speed, and so on. This data sheet tells you something, but it doesn't tell you nearly enough to evaluate the quality of the system. Peak SNR, it's basically, I would say, useless, because it only tells you what is the full well of your detector, or the square root of your full well detector. You need a lot more information to actually evaluate the real SNR in your images. And that's the purpose, or that's what I'm going to talk about now. Yeah, so traditionally, good hyperspectral data is as good signal-to-noise ratio as possible. But the definition of SNR today only depends on how much light goes through the system for different wavelengths and the detector specification. Yeah, the SNR is not good enough to evaluate the quality of the data. You also need to evaluate if the photon that actually reached your pixel is supposed to be there, right? Is it from the correct place in the scene? And that's where the big adder starts to actually come into your data. There are a lot of other contributions that are impacting the data quality more than the detector noise sources. And optical distortions are usually the largest contribution to the lack of spectral fidelity in each pixel. Yeah, the normal for a hyperspectral system that acquires dark current. This is the definition of the signal to noise ratio in that pixel. So you have the raw signal here with a scaling coefficient, which scales the digital number to photoelectrons generated in your pixels. Same here for the dark current. Then you have the noise floor and the photon noise here, and the noise or the noise floor and the noise in the dark current, which depends on how many images you are averaging your dark current. So I'll come back to that. Yeah, so this is a normal silicium detector in the visible range, where you can see here on the left side, this is the noise floor on a detector. It's showing every pixel element on the mean value and any pixel element on your detector with no light on the sensor, and then the standard deviation. This is for the visible part in our drone system. So here you can see you have a noise floor. There's a lot of pixels there, so probably the average is around 1.2 digital numbers, which corresponds to 2.37 electrons or photoelectrons. Then you have this very nice curve here. It's also the background in my LinkedIn profile, because this is how a detector should be. It should always be photon noise limited. And this is the photon noise curve. It's Poisson distributed, and it's basically that's the physical limitation of, or should be the physical limitation of any detector, right? Yeah, so basically when you're going up towards saturation here, you will have a noise, which is the square root of the number of photoelectrons generated at that digital value. Yeah. For as if you saw the SNR definition, you also had dark current. In silicium detectors, from 400 to 1000, there's very little dark current, and the dark current is also very stable, depending or no matter what exposure times you're using, and definitely for the airborne scenario. But if you're of course going up towards seconds and stuff for lab, then dark current also is a contributing factor in silicium detectors. But yeah, for airborne remote sensing and satellite and UAV, the dark current in the visible near infrared sensors are the same for all exposure times. Yeah, so but for shortwave infrared detectors, it gets the contribution of dark currents get larger the further up into the wavelength you go. So at 2.5, it's a quite large contribution of the dark current. So you need to cool the detector a lot. Our detectors are cooled to 150 Kelvin or stabilized at 150 Kelvin to reduce the dark current and the fixed pattern noise. But then you can see here you have a dark current that is larger than on the previous silicium detector, and this also is very correlating with the exposure time. So if you double the exposure time here from 1 milliseconds to 10 or to 10 times as much, you will get 10 times as much high dark current. Yeah, and here is a function for our SWE or a function for our SWE 384 cameras. This is dark current here. It's a little bit small, I guess, but dark current as a function of exposure time in seconds. So you can see, for example, at 20 milliseconds here, you have 15,000 digital numbers out of 65,535. So you're starting to reduce the dynamic range left, right on your detector. But of course, you still have 50,000 digital numbers left for the signal. And here it's in photoelectrons on this graph. So for shortwave sensors, dark current is extremely important to take into consideration. And also that means that the temperature of a system is also very important. So if your mechanics change temperature, your dark current will change. So that's important in how you are gathering the dark current and how you are correcting for it afterwards. Yeah, MCT detectors and in-gas detectors. In-gas detectors are used up to 1.7 micrometer. MCTs are used up to 2.5, also in the mid-wave range, right? Up to 5 micrometers. Those detectors have bad pixels. In 15 years ago, that was more than 1% of the pixels. Today, it's a lot lower than 0.05%. So this is a typical bad pixel map of one of our cameras, for example. So it's not too many. And as I mentioned, those pixel elements should have to be resampled, and we do it in the spectral domain usually, because the frequencies in the spectral domains are usually lower than the frequency in the spatial domain. Yeah, and then it's the total quantum efficiency of your hyperspectral camera. So a camera typically covers a large range. Our cameras, as you saw, this was the silicium range. Now this is the MCT range. So it goes from 950 to 2500. And to evaluate how well your camera is or how sensitive it is, you need to actually know the quantum efficiency of your whole camera. That means including all the optics, the dispersive element, and your detector elements for the whole range. And this is a curve for one of our 384 cameras. And then, if you remember the data sheet I showed in the beginning, I showed peak SNR, right? And the peak SNR tells you only what you can achieve basically in one band if you are adjusting the exposure time all the way up to saturation. Then because you don't want any of your bands to saturate, you have to keep the exposure time so low that you don't saturate any bands. And that's why when this curve here gets really important on the right? You want to have, you have the incoming light, you have the total quantum efficiency of your camera, and on the right side, you will get the signal to noise ratio as a function of wavelength for a given light source, which is the sun in our case. And then you will see that, okay, in this case here with the 100% flat reflectance, for example, if I saturate at 1100, I will have 200 in signal to noise ratio at 2.35. So then you know that for such a spectra, you cannot get 1150 in SNR, even if that's in the datasheet, right? So this curve is extremely important for the manufacturers, right, to deliver for any camera. And then optics and impact on spectral fidelity. So in a perfect hyperspectral camera, the spectrum captured by one pixel is an actual physical representation of the seen image by that pixel. So in this case, the SNR calculation done above is correct. Then it's enough with this one function, and that's all you need, and this SNR as a function of wavelength. But hyperspectral cameras are never perfect, far from it. Classical SNR definitions shown above assumes that the photon hitting a certain detector element is supposed to be hitting that element. To evaluate the real SNR in a scene, you need to dig deeper into the optics and the optomechanical architecture. So the largest optical contribution that compromises spectral fidelity in your data are spectral misregistration, spatial misregistration, and stray light. For some architectures, you have a lot of stray light. So let's go first into spatial misregistration. So as I said in the beginning, for a push-pull camera, right, you are spreading out the light, the spectral contents of a light in one dimension of the detector, and on the other you have the spatial dimension. So spatial misregistration means that you have different spectral sampling for different places, for different bands. Different spatial sampling for different bands. And then that gives you what you see here, a keystone effect. So let's say you are looking at a point source, a broadband point source, then ideally all your energy should hit on one column on your detector, while in real life it is not. So it's shifting over to the border pixels, like you see here. In any optical design, you have to, or if you want a very, very good system, you want a similar PSF, point spread function. This is the, yeah, so that maybe I should have defined that before, but so the energy from a point source, how that is distributed on your detector, that's your point spread function. So you want that to be similar for all wavelengths on your detector and for all position in the field of view. So if you have PSF variation, you're also going to get large errors in your data. I'll show that in the next slide. Of course, you have keystone plus PSF like you have here, and then something has disappeared. You also have blur, so the cameras can be very blurred relative to a pixel element. And the ideal case here is that all the energy hits here within one column. Yeah, we have a few articles on this. This is one of them, where we are evaluating 70 different cameras with different performance. You can see here that, and this is the relative error here on the left, on the y-axis. And you can see that keystone has the largest contribution to the relative error, while PSF also had quite a large contribution, and also different shapes of PSF. You have to read the article to see the scale on those two and for the keystone. But I will show you, dig deeper into the biggest contribution, which is keystone now. This is from another article where we have our UV data with less than 10% keystone, where we downsample it and we add keystone in different variations to see what kind of errors you get in the spectra. And you can see here the keystone as a function, also as a amount per pixel here. So, and the relative error here on the y-axis. So if you have 30% pixel keystone in your data, you have a 7% relative error in your data. So you cannot tell customers, right, that you have an SNR of 1,000 if you have keystone effects of 75% of a pixel, for example, that some suppliers have. Then you will have huge errors in your data. But if you are putting your camera into an integrating sphere and you are measuring the SNR, it will still look good, because the object in the pixel next to your objects, that's contributing to your spectral signature, is the same. So we are building imaging spectrometers, right? So we want to have effective pixel on the ground. So we want to be able to see two different objects next to each other. And that's when keystone is introducing a lot. So we also added here resampling. What errors are left after resampling if we are resampling the corrections, right? And you can see here that then if you have a camera with more than 15% keystone per pixel, I would say that you gain or you improve the data by resampling it. Of course, that also adds another question. If you have keystone in the data and you map that, characterize that during your lab calibration, is it stable when you fly? Because if it shifts, you will again add errors, right? So then you're correcting for a different keystone than is in actual in the data when you're flying. Yeah, this is just a cleaned up graph from the previous one, which is relative error as a function of keystone in your pixels. And all our classical cameras are below 15% here. Same with the UV cameras, while yeah, there are other suppliers of the scale on the right side here as well. spectral misregistration. It's similar. It's when you have different spatial sampling for different bands on the detector. So if you're looking, one way of seeing it, let's say you're looking on a laser, one narrow band light source, and that then should hit on a perfect row on your detector. While if you get SMILE, you will have a bend on this. That means that your spectral calibration or your center wavelength for a pixel on one side of the field of view is different than the other side. And that, of course, will give similar effects in keystone, but in the other domain. So you will get a contribution or a shift of the spectra. So let's say you are looking for a narrow source absorption features, for example, you will see a shift of that. An easy way to look at that, for example, in an airborne image in the Veneer range is to see how is the 760 absorption in the atmosphere. Is that different from one side of the field of view to the other? And for some images, it's a huge shift. Then that's a bad sign. Then it's stray lights. So stray light is basically light that hits the detector where it shouldn't hit the detector, right? So you have many different sources of stray lights. You can have reflections of mechanical surfaces, right? If you make an instrument in the shortwave range, anodized aluminium, it's a mirror in the shortwave range. So you can get a lot of stray light if you are not using proper coatings of your mechanical surfaces. It's the surface roughness of your lenses, of your mirrors, all your optical components. For example, in the visible range, when your wavelength is going down to 400, you have to have better surface roughness to reduce the scattering effect of the optical surfaces. And that's a very big problem in many systems, right? That you get huge contribution of stray light when you move down toward 400 nanometers. Yeah, so we measure this by scanning a point source through the whole field of view, looking at the energy, or basically mapping the PSF. We are scanning the PSF with 100 of a pixel through 6 pixels and seeing the shape of the PSF and seeing if or where the energy is distributed relative to the pixel next to it. That will tell you the spatial stray light. We do the same in the spectral direction. And another test, which I don't have shown here, is to actually use filters, long pass, short pass, band pass filters to block a lot of the spectral information and to see if you have any light where it's supposed to be completely dark. Well, this is quite a big problem if you have stray light, right? Because during the radiometric calibration, you are exposing your camera to a lot of light because you want to have as high signal to noise ratio as possible for the whole scene. So you're looking into an integrating sphere with a lot of light. So let's say you only have 1% stray light. That's a huge amount, right? And that compromises your response matrix and your quantum efficiency vector. So when you're trying to correct later on a weaker signal, it will be very visible. Then sharpness. So sharpness is not a quality parameter like the previously mentioned optical distortions, as long as the sharpness is similar for all wavelengths, right? So if it's not similar, then it's PSF variation. If it's similar, it's just a sharpness measure of your camera. But the sharpness measure is also very important because sharpness tells you, so if you go to the datasheet again and you say, okay, this has 1240 pixels, and some suppliers have a PSF that is 4 pixels wide. So that means that you have 4 times, if you look at the effective number of pixels, so the object you can resolute, you have 4 times lower spatial resolution than a camera with very sharp optics, where a PSF is only 1 pixel wide. So this is extremely important, and that's why we want to define like the effective number of spatial pixel and the effective number of bands instead of just spatial bands, the spatial pixels and spectral bands, because that doesn't tell you how sharp your optics are. Yeah, but there are pros and cons to having really sharp systems and really blurry systems. So if you have a very sharp system, spectrally and spatially, of course you can get aliasing effects, both spatially and spectrally on the scene, but you are gathering more information than a blurry camera, right? You can always blur afterwards as well. But yeah, some suppliers always have worse than Nyquist camera. So a Nyquist camera we define as where the PSF is larger than 2 spatial pixels or spectral bands. Yeah, we make very sharp cameras. That's our strategy for our industrial cameras. We make it sharp spatially, but spectrally we try to get close to 2 in full width f-max for the robustness of models across cameras. Yeah, so yeah, probably I mentioned something like this already. Yeah, so these are kind of statements that is when you are looking to buy a camera, you need to know what you are using it for. Are you using it for a research tool to detect what kind of specification do I need to do this? Or am I gonna use it in a quality control machine, sorting machine in the food, for example, and I want to buy 100 cameras and I want one model to work for all of them? Then you have different kind of cameras you should look for. And of course, what kind of pixels or what kind of objects, how big are the objects you're looking at? But for any given detector with a given detector pitch, the imaging spectrometer will always output more information with sharper optics. That's a fact. Then fact number 2 is, on the other hand, sampling the PSF with more than 1 pixel gives you more information about the PSF. But for a given detector, it will reduce the resolution of the system. Any given optical system will always output more information the more pixels you have per point spread function. So ideally, you should have many pixels per PSF and a lot of effective pixels. But this, actually, we are quite in the visible range. We are moving more and more towards that, right? Sony, for example, is making smaller pixels, very little noise floor, good detectors. So we can get always smaller pixels and a lot of pixels. Of course, you have to take data rate and stuff into consideration as well. But for the SWI range, pixels cost a lot of money. So if you buy a 384 times 288 detector, that has a certain price. If you buy 1,000 elements detector, that has a 5 times higher price. So it's yeah, pixel cost, and you want to have as sharp pixels per possible for the few pixels you have. So, but it's important for the customer to evaluate and for the users to know what they actually have. Yeah, I already said that though. So the effective number of pixels and effective number of bands is something that should be mentioned, right, in a datasheet or in a test report, like we supply with our cameras. So as I said, the effective number of pixels is or could be defined as the average spatial PSF width, or number of pixels. So the number of spatial pixels divided by the average spatial PSF will give you the effective number of pixels. And the same for the effective number of bands. And of course, we believe at Hyperspectral that when you buy a camera, price per effective pixel is a good measure or a good evaluation criteria. And then something about light sensitivity. In our datasheet, you can see that we had an F number. F number tells you how light sensitive your optics are. So in a hyperspectral system, you have a detector with a certain noise floor. So meaning that that's the limitation of each detector element. but it doesn't tell you how much light goes through the optics and how much noise is on the dark current. So if you want to know about what parameter that contributes on the light sensitivity, of course, it's your F number. It's the quantum efficiency of your whole optic. This graph I showed earlier tells you how much of the light coming into the camera actually is used to generate photoelectrons in the detector pitch or detector element. And then you're subtracting a dark current. You need to know how many frames is average there and what is the noise on what you're subtracting. And then you need to know the noise floor of your camera. But there is one measurement actually that tells you all this in one graph, and that is noise equivalent spectral radiance, which tells you basically what light needs to be added, or what kind of light source you need to look at to get a signal to noise ratio of 1. And that tells you as a function of wavelength your light sensitivity in radiance units, which is a very useful graph to evaluate how sensitive your system is. Yeah, and of course, then it's for any remote sensing system, you need a traceable calibration, NIST or PTB, for example. Radiometric, you need an accurate spectral calibration and accurate geometric characterization. I'm coming back to that soon. Yeah, spectral calibration. Basically, you are characterizing the center wavelength of each band in your camera. Many ways to do that. You can scan a monochromator through your whole wavelength range. You can use tunable lasers, specific lasers, spectral calibration lamp like mercury, xenon, krypton, argon, which have a lot of spikes. And you can also use mylar films and stuff like that to do this. The main thing is that you get a lot of very high accurate spectral sources across your spectral range. And of course, there are different dispersive elements. For example, if you have prisms, you have very unlinear sampling. If you have gratings, you have linear sampling. And yeah, of course, if you use other architectures like filters, for example, tunable filters or Fabry-Perot filter, interference filters, then of course you will have other issues with parallax and with the angle of incident and so on. But I'm not going into that now. Yeah, this is a typical setup. For example, you're also looking into an integrating sphere when you're doing the spectral calibration to fill the whole full well. And that might be, if you want to do that with a monochromator, for example, might be hard due to that you have very little light usually. So maybe a tunable filter, tunable laser rather, is a better option. Yeah, the output of the spectral calibration is basically a spectral vector or a spectral matrix, depending on if you are characterizing or if you have low spectral distortions in your image or not. And you should also have an output, which is always the accuracy of the calibration itself. And then, yeah, it just shows typical setup for the drone system when we are doing spectral calibration on that. And we are having a lot of bands or narrow sources across the whole spectral range. This is a visible and sphere system, so combined from 400 to 2500. Yeah, then the radiometric calibration. We use not the same source usually. When you do a radiometric calibration, it's extremely important that you have an integrating sphere that is uniform, right? All non-uniformities of your sphere will means non-uniformities in your camera. So typically those integrating spheres are a lot larger to make it better, or make the port in the front smaller relative to the size of the integrating sphere. So the goal here is to generate a matrix that tells you basically the response differences of every pixel. So this is can be a function for your output digital number on your every pixel element, right? So you have here the number of photoelectrons, the total quantum efficiency of your system, the response matrix of your system, a scaling factor here, basically is the dN per photoelectron, and then the dark current. So during the response matrix or the radiometric calibration, you are gathering R here, which is a combination of QE and RE. And what we do in our calibration is that we separate those two terms because we want to be able to do only response correction and not correct for the quantum efficiency. And there are reasons for that, because usually, or when you correct for the quantum efficiency as well, you might go outside your bit depth, for example, which is a question for another time. Maybe for example, if you're doing real-time processing and stuff and like that, then you might want to keep the baud rate or the data rate low. So then you might want to do the QE correction on the receiving part instead before you send the data. Yeah, so the output of this calibration is then a QE vector and a RE matrix. So that means that you have to do the spectral calibration before you do the radiometric calibration, of course. Yeah, and this is a function to describe your radiance level as a function of digital number, dark current, Planck's constant, the speed of light, and the quantum efficiency, RE, scaling factor, area, entrance aperture area, solid angle, your spectral sampling, and your center variance of every band. So so basically the background here, we calculate for every frame in your image during operation, right? Well, QE and RE is coming from the radiometric calibration. Delta lambda and lambda is coming from the spectral calibration. And then you have a traceable calibration. And of course, it's important to mention to what accuracy is your traceable calibration. And that usually, of course, depends on the stability of your system, but also, how much you've paid for the integrating sphere. Because you can get that with 20% accuracy, you can get it with 1% accuracy, depending on which supplier you use. Yeah. For our systems, that's from 400 to 2500. The light source is typically tungsten halogen lamp because it's broadband and it covers the whole spectral range and it's stable. Spatial uniform, I already mentioned all this. Yeah. Then we go to geometric characterization, which is very important in what we are talking about here. When we're going to do ray tracing, we're going to do geofencing, we need to know in what direction is all the pixels from your camera pointing, right? I've seen suppliers that just say, this is our F number, this is our field of view, just calculate it. And of course, then this is not possible in a hyperspectral system. You need to, with a very high accuracy, measure the center of gravity of the PSF for each pixel to be able to tell where it's pointing with a sub-pixel accuracy. And that's your typical sensor model, this file. This is our setup. It's an old image, probably 10 years old. So it's not completely like this today, but it's very similar. So we scan the camera across or along the slit. So we can map the position of a point source in a collimator all over the field of view, right? And based on that, and based on having a very high accuracy rotation stage with a very sensitive encoder, here is 0.79 arc-second resolution, which is better than 1/100th of a pixel. You can basically make a sensor model telling you the direction of each pixel. And this is an example from an error of linear fit. No, not linear. I don't know the polynomial again, but it's a fit to the measurements data for a 3640 camera. So it's the pixel size for this one is 0.44 milliradian, so it's close to 1/5 or less than 1/5 of a pixel. And the last thing, I think, before I go to operational and we can take the first round of question is, of course, the stability. Yeah, of course, if you have a traceable calibration and this only is stable in the lab when you're at 25 degrees Celsius and it starts shifting when you get gradients and so on, then it's quite useless, right? Then you cannot say that you have a traceable calibration. So during the design phase of your camera, you need to take that into consideration as well. How is temperature influencing your design? How is pressure influencing your design? And so on. Vibrations, EMC. So all our cameras, even the one we sell for a lab system, goes through vibration testing. So we do calibration before and after vibration testing and so on. So assure that this is stable. And also climate chamber testing. Yeah, unaffected parameters of thermal, pressure, vibration, EMC can be sharpness, distortions, granulometric accuracy, spectral shift. So the band can shift, right? And the geometric characterization can shift. Okay, then maybe we can take a round of questions on the camera side before we go to some operational noise sources.
Yeah, maybe we take the questions and go for a short break because you are speaking 45 minutes now.
One more time.
Yeah, I mean that let's take the questions and then go for a short break, like 10 minutes.
Yeah.
Yeah. Okay, so I think there are some questions on the chat.
Yep.
So how frequently do you conduct this calibration?
How
frequently, how many times do you conduct this calibration?
No, so this is done so when we send it out. We have had the airborne system that's been 10 years in an aircraft without having to redo the calibration. But when I'm looking at, so I'm actually on the background here before this talk, processing the data for the session tomorrow, looking at Agnar's camera. Has been standing like 4 or 5 years, hard mounted like to the floor in this passenger aircraft without damping. I see some slight striping in the image, which is usually caused to that dust has. So we do all this in a flow bench, right? So when we mount everything together to make sure there's no dust. But if there is a dust particle that hits the slit, you can get the striping in the image. So yeah, so if you start to see any striping effects at all after some years of operation, it's a sign that that you should recalibrate it. The operational airborne customers that we have, they send it back every 2nd year just as a precaution. So we do a recalibration and yeah, just a recalibration of the system. Yeah, so that's typical.
Yeah, so the second question is, what is the practical process used for conducting this calibration? I think you have shown the calibration of one experimental setup, but is it for every parameter like spectral, spatial calibration?
Is it for
all kinds of calibration, like geometric, spatial, and spectral calibration?
Yeah, so actually that's a good question, because there is this P4001 IEEE project now for making a standardization, actually, which of course we at HiSpace is heavily involved with making a standard for calibrating and characterizing these kind of systems. Push broom is the main object, but we try to make it so it will work for many different architecture. And there now we are in the last year of making this standard, and now we are in the process actually of defining the test equipment to do this for all architectures. But it's very similar to what I've shown you now that will be used.
Okay. And the last question is that how is calibration done in satellite sensors? Is it automated in regular time?
Yeah, so it's very, very similar. So as I said, DLR, we have NASA, we have quite a few customers that are using our system for simulating space data, and their calibration labs looks very similar to ours. So of course, everything is larger. For example, the Lars lab, which is calibrating Nmap, is a huge integrating search, probably 2 times bigger than ours, right? And but they have the same spectral measurements, the same geometric measurements that we are doing. So it's similar, but one consideration for space data is that you have to have full control of how your optics change with temperature and pressure, right? So it's going to be different from doing the calibration on in a lab than in orbit. So typically satellite systems have some onboard calibration to map the changes, right, when it's launched, which is normal, and which we also had in our big military project, and will also of course be part of our ESA EOD platform.
Thank you, Trond. And any more questions from the audience? These are the questions from the chat box. But if you have more questions, you can raise your hand.
Yes, Sheila, I can just comment that we will send our spectrometer in for calibration this fall.
Okay. Yes.
But this
Yes,
can
but-
also be, just so you know, when you see some slide striping like this, which I saw, especially you don't see it in an urban scene, but if you're flying over water, for example, where there's quite a little light, you can see it. You can fix that. For example, if you have flying over clouds, for example, you can fix that by having a de-striping algorithm being made when you're flying over a uniform area, and you can add that correction to your RE matrix before you do the processing, and then you remove the striping. But because these things are not something that is changing from every flight. So it's so it's possible to correct for if you see it and you want to still have non-stripes in your image, right? But it's very seldom. So I was actually surprised seeing this at Agnar's camera now, because this is it is typically not. But of course, when it's flying every day in the floor without damping, this can happen.
Yes, I think so there was one more question. Can you please share some relevant material in advance to every time on your lecture schedule? Maybe we will share some material once the lectures is done, and I think Trond and Agnar will provide some literature on that if you need more basic information.
I can share this presentation afterwards. So
yeah. But I think that he's asking for more material for understanding. So
of course, I'm not saying everything we're doing here, right? I'm saying the overview, because some of them is like our intellectual property as well, because always we are doing stuff. We don't want to share everything, but what I'm sharing here now is what every supplier have to do, right? How they do it, can be intellectual property, but but I can share. We are quite open, right? So we can share a lot, but not everything.
Yes, and one more question in the chat box: what flight precautions are generally taken to avoid any physical distortion to the onboard sensor?
What kind of precautions did you say? What?
Yeah, what kind of precautions you take when you are conducting a flights
Also,
to avoid some physical distortion in the sensor?
Also, let's say you want to put your system on an aircraft and you want to fly it for 10 years without recalibration. I would say that's not a problem if you dampen it, right? If you have it on a passive damped platform or even a stabilized platform. Of course, that's a lot more expensive. That's a way to change or reduce the risk of anything happening. For all the optical distortions that happen due to temperature, pressure, EMC, and vibrations, you are quite, that's based on your design, how you design your hyperspectral camera, how temperature is distributed in your camera, how it's affected by having an open hatch and you have cold air on one side of the system and not on the other. all that part is extremely important in the optomechanical phase and in design your optics. You have to, yeah, that's a really, really important part of designing any airborne platform. So, but if you have a bad platform or bad camera, you can try to correct for it, but it will be quite hard, because when you start a campaign, you open the hatch, it's or it's always open, depending on your system. It will change a lot during the first couple of hours, for example, and then so you would constantly need to do stuff if you have an unstable platform. So yeah. So I will now talk about the operational sources of errors you can have. And I just wanted to show just an example of an auto-rectified image from, this is from actually the same system, or not the actual same camera, but same model as Agnar is in the SIOS aircraft, or the NORCE aircraft. The 5 flight lines here done in Italy, in Parma. In this area here, or in this flight, there is 900 meters different on ground elevation. So we're flying LiDAR together with the high specs. This is also together with sphere, so it's a merged cube with near and sphere. And when you have full control of geometric, your sensor model, your elevation model, your bore site, your height reference, everything we're going to talk about now, you can get images or auto-rectified images where you merge together 100 flight lines on a big area without any GCPs on ground, and you cannot see the stitching between the flight lines because of the accuracy you have in your bore site, in your DSM, stability of your system, and so on. So this is the goal here, right? To have a system that you can fly and where you can always do direct referencing with a sub-pixel accuracy. Okay, let's move on to the processing flow. To understand where we can get error, of course, you need to understand how we process the data. So this seems very advanced, but it's not, as I said in the video that I showed earlier about real-time processing. All this can be done in real time today, to this stage, in the future, to reflectance as well. So HySpace Air is the software that runs on your drone, on your airborne system, which is capturing the data in a raw format. So we never do any processing on the raw data, so we always keep the raw. And then there's a binary header in each binary file that contains all this calibration information I mentioned earlier. It contains dark current before and after each acquisition. Depends have the spectral vector, quantum efficiency vector, response matrix. All that is part of the binary header. So that you don't, if you have the image file, you have everything. Then you do HySpace Rad is a software that do the radiometric calibration and spectral. So you will get an sensor radiance file, unrectified, of course, after you have run it through that. Then, yeah, our systems is compatible with all kind of navigation system. The only criteria is that it has an event input, and all navigation system has an event input. This is for a planning system. A planning system uses a software called Pushback for post-processing the navigation data. So then you would take the raw files from the planning system after you have flown, put them in, import them into Pushback, process it, and what you're then getting out is an event file. That's an event coming from the HySpace system, which is synchronized, of course, with every beginning of each frame of our camera, of our images. Then you have a 200 Hertz INS output. It can be 400, can be 100, depending on the navigation system. But I usually prefer to use systems that have a little bit higher frequency than the cameras. Then to get really good results, you need to shift since this pulse is synchronized with the beginning of each exposure. You, as Agnar also said, you have motion blur, right, due to that you're not exposing exposing your detector infinitely low, right? You're using a specific exposure time, and then the timing is shifted to the mid exposure. And that's done in HyperSpectral. And then HyperSpectral outputs one text file with XYZ role play shading for every frame in the HyperSpectral image. Parch takes that in to do the georeferencing together with elevation model and sensor model. And there's missing one box here at least, is the bore site file as well. Based on that information, Parch can make an auto-rectified hyperspectral radiance image. And at the same time, it generates all the information needed to do the atmospheric correction later on. So it does generate a scan angle file and so on. And then you can run ATCore or DroaCore, which is the software for drone, and you can get reflectance data. At sensor radiance, so that's converting the raw digital numbers to the at sensor radiance traceable to PTB and NIST that I just described earlier. I covered this already. I covered this. I also already mentioned that. This as well. And here's the example of the Parma data. This is how it looks. This is enhanced in Envy, right? So if you have worked with Envy before, you know that enhancement is based on the scene. So you can enhance it once you open it, but this looks different color-wise because it has snow up in the corner, while this doesn't have any snow. So the intensity is so it looks better, but you can enhance this so it looks like this, right? But this is how it looks unrectified, the data. And then this is the elevation model used here from a LiDAR. I think it's Leica, or was it a Regal? And then you can georeference it and mosaic it to one area, right? And you have the sphere data. Same area, they are running in sync, the Veneer and sphere camera, so that you can, it's very easy to co-register the Veneer and the sphere also together. So you can get a full cube from 400 to 2500. And here is, here also need to, so if you want a full cube based on two systems, you need to consider what kind of optical architecture they are. So if you have two different cameras, then you have two optical axes, and then you need to make sure that the supplier has full control of bore sites of each of them, and also how they are timed relative to each other, so that you will have a, for example, our system is timed with, let's say, the frequency f with the Veneer and f divided by 2 on sphere. So we have a GSD that's matched to that, which is makes it easier to co-register it afterwards. Some optical architecture, like our Odin, has a common slit, meaning that both Veneer and sphere are looking at the exact same state on ground. Then again, you need to take into consideration that you trigger the cameras with the same pulse. You also need to take into consideration that if you use different exposure time for the Veneer sensor and sphere sensor, you will have spatial distortions in the along track direction due to that the mid exposure will be different. So it's a lot of consideration you need to take into account. For our drone system, we do it something in between. So we deliver a full package, right? V and S with navigation system inside, where we co-align them. That means that we are aligning the optical axis so they are completely parallel, but they are shifted by 75 millimeters apart, but they are parallel. That makes it, because then you will not get any co-registration error in the along track direction. And if you have an accurate DEM, you will get a very good co-registration also in the along track, across track. Yeah, so let's go to the elevation model. So for airborne, at least when I was doing the airborne the first time in 2003, like if you had an elevation model with 0.5 meter accuracy, this was very good. Then you will get extremely good data. And that's true for 1,000 meter plus. You can get good accuracy with a 0.5 meter elevation model. But if you're flying on a drone, for example, and you're flying below 150 meters, 0.5 meter is not very good. And I think I have an example later on here, calculation example, where you can get, if you're flying at 50 meters with our drone system and you're 0.5 meter error in your elevation model, that gives you 7 pixel shift in the overlapping region. Yeah, so when should you use an elevation model and when should you use a surface model, right? An elevation model is basically if you are processing a point cloud from a LiDAR and you're making an elevation model, the software you use, there are many software for this, you're using is filtering out the trees, right? Or everything that has a huge spatial frequencies. So you're basically generating the ground, not the surface model. For airborne images, flying 3,000 meters, for example, it's probably not a big difference because the height of the trees are low relative to the altitude you're flying. Same for space, of course. But if you're flying drone at 100 meters and you have a 20-meter high tree, then it's a huge difference, right? And you have to use the surface model. And when you have to use the surface model, then you have to have a lot better control of the bore site, of the your navigation system have to be good, or else you will not have a LiDAR system and a high specs or hyperspectral system that's matching. And what's worse than then you can go back to the elevation model, because if this is not matching, it will be correcting for a tree where there is not a tree. So it will give you very wrong results. So that's important. And here is an example of 2 images. I think they also are from a Canadian customer. I seem to be drawing on my screen here. I'm not sure. I usually use Teams. Let's see, can I remove that? Clear. Yeah. So on the right side here, I've used a elevation model to rectify 2 flight lines and mosaicing them. You can see here you have this trail here. It matched very well. If I could have zoomed in, you could have seen that you don't see the overlap here, except you see the BRDF effect differences only. Because we come back to that, right? You are flying in each 2 different directions here, right? But you have a good matching here, but you see in the trees, you don't. You can see the tree suddenly stops, right? So you don't have good co-registration here because you're using the ground elevation to do the ray tracing. While here you're using the surface model and you have good overlap on the ground and in the trees. But you're of course you can see some dark spots here and there. That's due to that there's a very steep hill or in your surface model, right? And then you will not have data. Another example. The reason I use this example as well is because this customer actually has planned their flights relative. So when you plan a flight, which I think Agnar will mention in the next session, you have to take into consideration what kind of overlap you want between the flight lines, depending on the altitude you're flying from the ground. So this customer has done this, but it's not taken into consideration that I think this is flown at 60 meters and the trees are probably 15 meters maybe. So you can see when you use the elevation model, you have overlap everywhere, but you have the co-registration problems between the flight line. While here, when they use the surface model, they have the co-registration they need between those 2 flight lines, but here they have a gap because they have planned it that the distance to the ground is higher. So then you get better overlap, while now the distance to the ground is lower and actually the flight lines are not overlapping at all. So this is important to at least if you're flying UAV systems, to plan it. Yeah, this is the example I mentioned that if you're flying at 50 meters, our pixel size is 1.3 centimeters. And if you have a half a meter error, you are getting 7 pixel in the elevation model. You're getting 7 pixel error in the overlapping region. So when you're talking about UAV system and bore sites, we are usually talking about millimeters in bore site accuracies rather than centimeters. So everything gets, that's why we are supplying LiDAR system and photogrammetric systems that are mounted on the UAV systems, because typically we had customers, right, that have a huge demand for accuracy, and then they come with a 30-meter resolution elevation model, and yeah, then that will not work, right? The image will look good, the rectified image will look good, but co-registration between flight lines will never work with such a coarse step. Base station is important as well to get good data. There are, if you use a planning, for example, they have a lot of solutions for this. You can download the publicly available base stations if you are close to one. If you're far away from one, you can have a smart target that's a portable one. You just bring and you put it in the scene and start it. They also have a service that is quite expensive. It's called PPRTX, which uses a service from Trimble to generate everywhere in the world a virtual base station, which is a very good solution. If you are using real-time INS solution, you can use Omnistar or TerraStar to get corrections in real time as well. This, you only need that if you have a high accuracy for the absolute, or high specification for the absolute accuracies in the GPS position. The image will still look good. The rectified image will look nice even if you don't have the absolute high accuracy. Yeah, this is just some sales pitch for it can be that the Mjolnirs can be coupled with any device since it has availability to trigger and time other external equipment. But an important thing is that you need to time your data, which I'm coming back to now. One big problem is actually that you don't have full control of when the mid exposure of every frame is relative to the GPS or INS data. Another, I will go have some slides about that now. The other is that your INS data is not good. For airborne data, when Agnar goes out flying, if he hasn't done a lot of turns before he goes to the campaign area, he flies an 8. This is to align the INS. That gets the INS fast into a very good alignment status and very good performance. For drone system, for example, if you're flying for 30 minutes, you don't want to spend a lot of time on that. So you have a different procedure. You fly up, you fly straight very fast for 20 seconds, you stop and you come back, and then you're aligned. So you use 40 seconds to align it. You do your campaign, you do another alignment before you land, and then you're done. To fast get the INS system to a very good state. Yeah, so Agnar, I think, will show something about this tomorrow or later today when he's processing in postback. And then it's, as I mentioned earlier, co-registration of veneer and sphere cubes. If that is of interest, then you need a good elevation model or surface model. Stabilized platform can help. You need a good sensor model. You need a very good bore site calibration. And yeah, you have to take into consideration on the sampling and motion blur. Yeah, as I said, the two cameras should have the same mid exposure or the same blur. This is a typical airborne installation. Not similar to, so Agnar in the Dornier, you have a little bit different because you don't have a touch screen directly coupled to the high-specs computer. You have a TCP/IP interface that's controlling the software. But this is a normal one where you have a DAU, data acquisition unit, basically a special made computer. It's connected to veneer and sphere camera, both with camera link and a mil spec cable that has the triggering power and stuff like that. communication. Then you have Ethernet, for example, to the navigation system. You have a BNC that's sending the event from the frames that is timed on the navigation system. You have a GPS antenna connected on the roof, and you have an IMU somewhere, which typically you want to have as close to the camera as possible. Then you have a touchscreen with a touchscreen interface to start and stop acquisition. Of course, that can also be triggered automatically from FMS or from TCP/IP commands or serial commands. Yeah, as I said, we have here in this MIL connectors here, we have the triggers. So the frequency generator or the trigger card that we have made is inside the DAU. That's controlling or making sure that all the systems are running in sync. And that's also generating the event input to this one. So here I show it for the UAV, but that's the same for airborne systems. So basically, different navigation systems have different max frequency they can usually time. But almost all navigation systems can time any pulse with a 15 nanosecond accuracy. So what we're doing then, we have a frequency generator card triggering the veneer. We can trigger then the sphere depending on which optics you have with the same frequency divided down by any factor. And then you can again divide down by any factor. For the UAV system, it's 8 to the uplink system, because the uplink system has a max frequency of 50 Hertz on the events. And then in the high specs nav that I mentioned earlier, we are basically getting the timing back and doing the resampling to the mid exposure. This is extremely important that this is done properly. There are some suppliers that are sending one pulse in the beginning of a flight and one pulse in the end to sync the clocks, which can be not very good in the long run. Of course, you need a good INS system, but you don't want to pay too much. So you need a good performance for what you need or for your area, right? So for example, in a drone system flying on a copter solution, the APX15 is a very good choice. You can get down to 2 to 5 centimeters in position, 0.015 degrees in, not 25 degrees in roll and pitch, which is 1.2 pixels in veneer and 0.6 pixels in sphere, and 0.08 in heading. This is good because you can get it quickly aligned. It will be good for short flight lines, let's say less than 5 minutes, because then the heading doesn't drift off. And then, but it will not work, for example, if you're going to mount our UAV system on a fixed wing aircraft, or a fixed wing UAV, and they want to fly a 20-meter long flight line, a 20 minutes long flight line, then this is not good enough. Then you need a better IMU that can be better for flying without taking turns. So there are APX20, there are the one that is in the Dorney area is a POST-AV 410, a very good system where you can fly for 20 minutes and the heading doesn't drift off. So yeah, it's important that you have a system that matches your platform and your needs when it comes to navigation system. And it's also always a matter of price, right? You have some very, very high-end system that costs 200,000 euros that can use the rotation of the Earth, right, to calibrate, while some need movement of the platform. Yeah. And then this actually goes also for airborne systems when you use stabilized platform, but it's very relevant for also for UAV systems when you use gimbal. So as Agnar is also going to mention in the next session, we have to measure the level arm. That means the position of the GPS antenna relative to the IMU to be able to move this position from the antenna down to the position of the IMU and then to the camera center. And this is if you're flying just with dampers or hard mounted like Agnar does, then you know the level arm very well and it will always be stable. While if you fly with a gimbal, during flight, the gimbal will always keep the platform stable while the antenna is standing on the platform, right? And then you'll have a dynamic level arm. If you don't compensate for that, your limitation of the X, Y, and Z in the APX15, for example, will be 9.5 centimeters approximately, what we have found in all our systems. But then there's a solution for that as well, adding a second IMU to the platform that compensates for the movement of the navigation system. So it always calculates where the position is of the antenna relative to the IMU and the camera, which is a good. Then you get it down to 2 to 3 centimeters, also with gimbal, right? Because gimbal is important. I'm coming back to why gimbal is also important for copter solutions and maybe not so important for fixed wing solutions. Yeah, and as I said, that's also why we are selling LiDARs and photogrammetric solution with our systems, right? So that we can can use the same navigation system, the same dual IMU setup to do all this only once, right? So yeah. And then the gimbal. So this is a flight we did in China, quick after each other, just to test how the pixel field of view looks on ground with and without stabilized platform for the same conditions, right? So when Agnar is talking about motion blur in a fixed wing aircraft, because a fixed wing aircraft is relative to the frame rate of the camera, is moving quite smooth, while an octocopter, you can see, is not smooth at all. So your pixel size on ground when you're not using a gimbal will be very much distorted relative to when you're using a gimbal. So that's why gimbal is highly recommended for all copter solutions. Helicopters, you are okay with the damped platform. But optocopters, this 25 kilo UAV, we definitely recommend gimbal. Then it's the bore sight. So dietary referencing, that's when you are georeferencing your data without any ground control points. So that means any points on ground where you know exactly the position. To do dietary referencing, you need an accurate bore sight calibration. And as I said here, a bore sight calibration is actually finding the roll, pitch, and heading or your offsets between your coordinate system of your sphere camera to a vernier camera if you have 2 cameras, and then finding the roll, pitch, and heading offsets from your master camera vernier to the IMU system, right? That's, if you have those offsets, you can correct for this displacement that you have in the INS data, which is very important. Or else you can be actually, if you fly at 1,000 meters, you can be 30 meters off just because you don't have the bore sight angles, or even more, depending on how badly you have mounted it relative to the IMU. And you can never mount. So we had some customers, right, that did a bore sight calibration, took the camera out, but they placed it back in the same position and used the same bore sight. Of course, that's you can think that you have put it back in the same position, but you would have to need to put it back with the camera Agnar is using 0.0015 degrees in all 3 rotational axes, which you cannot do. So you always need to do a new bore sight if you're taking the installation out and back in again. Yeah, so to do a bore sight, that's the same for airborne and UAV. We fly across. So this here is on a shooting range that we are flying every week when we're delivering UAV systems. So we have a lot of GCPs on ground, and we are flying across over those GCPs, and we are flying each of the flight lines in this crosshair in both directions. So we're getting 4 flight lines in all the bore sight flights. I will go through this tomorrow, other options as well. But then based on that data, you can actually calculate the bore sight angles of your system. The reason you do 4 is because you want to do 4 bore sight calibrations to check for consistency. Because if the bore sight calibration when you're flying in that direction and that direction is different than the opposite way, then it means that you have some kind of quality issue. Either it can be that you're selected the wrong surface model. It can be that you have a level arm is not correct. It's 5 centimeters off. So when you turn, you get a 10 centimeters error, right? So there can be a lot of things that are wrong. And that's why we always do this, to be sure that we are delivering consistent bore sites to the customers. When we do the bore site calibration before, which we do for all UAV systems, but for an airborne system, for example, of course, we have to install it. So during our 3-day training, we install it the first day, do a bore site flight the first day. Second day, we do the bore site processing for the customer, and usually then fly in the evening with a campaign. And then the third day, we do direct georeferencing based on the bore site to show the whole process. Yeah. And the most common errors when working with customers around the world, I've probably done, I don't know, 50 installations around the world with different kind of aircrafts and different kind of elevation models that the customer have or have gotten from, yeah, publicly available or something they made themselves. Then the most typical error is actually that the height reference is wrong. They have either, if it's ellipsoid, it's okay, but typically all INS systems, right? They give out nominally the data in ellipsoid height, while all surface model is usually delivered in a geoid. That's locally very good relative to the country that you're in. For example, Svalbard have a very special one. And yeah, and then you need to know that, right? So if we are processing with the high specs data in ellipsoid and the DEM in a geoid, for example, the normal EGM 2008 in Norway is 38 meters different from the ellipsoid. So you will get huge errors in your bore site and in direct referencing if you're not working in the same height reference. So yeah, that's just, and in postpack, for example, you can export in a lot of different geoids, so that you just need to be aware of that you're working in the same reference. And the same goes for X and Y, right? You want to have the same datum, same projection. So if you use UTM, for example, you need to know that the datum is the same for your elevation model and for your high specs data. Or if you use an orthophoto, many people use an orthophoto to also do bore site, then you need to know that your orthophoto has the correct datum. That's you. Yeah, and then is the forget. Okay, that's a bit bad wording, but that the difference between DEM and DSM can also be, for example, if you're doing this from an airborne system and you're using a building, corner of a building as a reference, can be okay if you're flying high from an aircraft, but yeah, from a drone system, you are selecting it and it's getting the height from the surface model or elevation model, then it's very easily 3-4 meters wrong because you're not hitting the correct pixel on the corner. Yeah, I will show a bit that tomorrow for the practical session. So yeah, so as I said, so we are finding the offsets here between the coordinate system. Basically, at the end, right, you have a Earth coordinate system that everything is resampled to. And the direct georeferencing means that you can do this without any need for GCPs on the ground, which is what anybody wants at the end, not to go out and measure or have to have an orthophoto to do the auto rectification. So conclusion on optical considerations. High performance time tagging of all frames are always needed to get good georeferencing data. And here is different. Here, this is important, right? The difference is here now based on what you need as an end user, right? If you want good co-registration between a veneer and a sphere camera, you can do that with a high accuracy sensor model, a high accuracy bore sight, and optomechanical stability. But you don't need a high accuracy elevation model to do that. But if you want to have good overlap between flight lines, meaning good absolute accuracies on the GPS position, you need also high accuracy DSM/DM and high altitude INS data, sub-pixel. Yeah, and then at the end for this, another very important operational parameters that I almost don't need to mention it because it's obvious, but I'm doing it anyway, because after you have selected the frame period relative to your flight altitude and ground speed, I think Agnar will mention something about that later, about the flight planning. You must optimize your integration time to get the best possible synchronous ratio in images. If you're doing oversampling with a lot of factors, or a lot of oversampling with a factor 5, for example, you might never go into saturation. But then that's okay, because then you can bin those images together afterwards in the post-processing, right? But if you're using an exposure time where you might go into saturation, or you're flying with snow, for example, it's important that you increase the exposure time until you saturate on your scene of interest, and then I would say decrease it by 15%. Then you're close to saturation, but you're not reaching it. Then you will have the optimal SNR in your images. And if you're flying for 8 hours, starting at 10 o'clock or starting at 8 o'clock, this has to be adjusted according to the sun angle during the day, right? When the light intensity changes. Atmospheric correction. I will not go into in-depth about that, but there are many different solutions out there. We have specialized in ATCOR and DroneACOR. So basically, it's the process of going from at sensor radiance to reflectance. So you're removing the influence of the atmosphere. Yeah, many applications you can work with radiance, but a lot of applications you need reflectance. So you need good atmospheric correction. There are some, I know actually GFZ has been doing, I don't know the status of this now. I remember Max there had something he called high LiDAR, where he's using multispectral LiDAR to actually, and looking at the reflectance of the LiDAR active pulse, right, to say something about the atmospheric correction. It's also a smart thing. And this down here is 2XL in UK doing something, I don't remember the name of it. But as I said, there are, you have Flash in Envy. There are many different solutions there. You can do a simple empirical line correction if you have a FODIS on your drone, right, measuring the radiance from the sun while you fly. You can have something on ground, measuring during your campaign. So there are many options for this, and many pros and cons on the different softwares and different ways of doing it. But we feel that ATCOR for airborne and DroneACOR for UAV is a very good solution. And then 2 more slides. As I mentioned earlier, you have the IEEE project that is making a standard for characterizing hyperspectral cameras in the spectral range 400 to 2500. This standard will cover most detectors and optical parameters that I have mentioned in this presentation, but not on the operational side, but on everything we had before the break. And the standard will also present a way to visualize this in a datasheet, so that when you open a datasheet now, it might be 1 more page, but you can actually read about the efficient number of pixels and the efficient number of spectral bands in your instrument. Yeah, and NEO, Hyperspecs, and also other manufacturers are part of this group to define this standard. So of course, we at Hyperspecs hope that everybody will start to use it very soon. So to sum up, it's impossible to say something about the quality of a system from the top level specification. Detector noise sources, which are typically not the largest noise sources, but they are usually the only ones that are mentioned. But they are not the largest in a hyperspectral system. Optical distortion, which cannot be read from the datasheet, are the largest contribution to reduce spectral fidelity in your data product. And it's important for end users, the people that are working on the data, right, to know about these noise sources in the data, because then they can understand better the potential and limitation of the data product. And then, of course, that makes it also important for manufacturers. That's why I hope that people will start to use this standard to inform potential users and buyers of the camera. the performance in relation to all the above mentioned quality parameters. So, and at the end for operational, even if you have a very good hyperspectral system, it's still possible to operate it in a way so you get not optimal, and it will compromise the quality of your data. Thanks.